Okay, we want to talk about this idea of free variables. They're going to be very important. Solution, so we just start out with a simple algebraic equation that we can easily solve. 2x plus 3y equals 6. Okay, well, we solve that, we get y equals negative 2/3 x plus 2. Our solution is going to consist of all possible ordered pairs x, y that satisfy this, which is, of course, equivalent to this. To represent those points, we can draw a straight line, as we know from early algebra and beyond. If x equals 0, either through this one or this one, we can determine that y equals 2, sorry. So that we have the point 0, 2 on the graph. Okay, if we use this, the slope-intercept form, this says, of course, that the y-intercept is at y equals 2, and that the slope is negative 2/3, which means that for every 3 units we go over, we go down 2 units. We can get from 0 to go over 3 units, down 2 units, 3 0 if we wish. Or we can simply use the fact that when y equals 0, we easily get x equals 3 and use the 2 intercepts. Either way, we get the graph of the function. Now that's just simple early algebra. So we certainly understand that, and make sure you understand it in the way I explained it. Okay, in in a linear algebra course, we don't confine ourselves to letters, different letters for the axes for our variables, because a lot of times we're dealing with many variables. Okay, we want to at least be able to write down what we're going to get and what we're going to need to be using if we have 500 variables. So we're going to use x1 and x2. We can't use different letters for 500 variables. We're going to run out of letters. We're going to forget what they look like. We're going to forget what they mean. But if we use subscripts, we know exactly which variable we're talking about. Okay, so the solution of this equation, which is the same as this one, except I've used x1 and x2 instead of x and y, it's going to be written a little differently than the way we did this. We're not going to use slope-intercept form, because that doesn't help us a lot when we get into higher dimensions. Excuse me. I just started talking. I don't know, weather. So anyhow, when we solve this, I'm going to choose to solve it this way. And you'll see later why. Actually, this is kind of a review, so you probably already know, but we're going to solve it in the form x1 plus 3/2 x2 equals 6. And then we're going to regard x2 as a free variable. There are many combinations of x1 and x2 that make this true. This being essentially the same equation as this, any xy on this line is going to satisfy this. If we use x1 for the x coordinate, x2 for the y coordinate, this is what we get. So we're going to say that there's a free variable in the sense that, just as, let's say in this form, we can choose any number for x and we're going to get a number for y. That makes x a free variable. Now, of course, we could do the same. We say, okay, let's let y be the free variable. We'll choose y. We're going to be able to always get x. Here, we're going to let x2 be the free variable. And we're going to give the free variable a different name. We're going to call it t. We're going to treat it as a parameter. Okay, so x is a free variable. We're going to call that variable t. Then, well, x1 plus 3/2 x2 equals 6. If x2 is t, we get 3/2 t here, subtracted from both sides, and we find that x1 is 6 minus 3/2 t. It follows then that the ordered pair x1, x2 written as a column vector now is 6 minus 3/2 t, t. In other words, x1 is 6 minus 3/2 t, x2 is t. Now we can rewrite this variable, or this vector, as 6, 0 plus negative 3/2 1 times t. We've essentially separated the terms with t on them from the terms that don't have t. And since you know how to add column vectors, it's very obvious that this is correct, that this represents this. If you add these two, you certainly get this. Okay. The meaning of this -3/2 1t is going to be just looking for the right color chalk here, is going to be represented here. That's the vector -3/2 1. And I've made unit marks on the axes. This is -1, this is 1, this is -1, this is 1 on the x and y axes respectively. So there's my vector -3/2 1. Now, if I multiply that vector by t, I make it longer or shorter, and I can make it as long or short as I want. I can also make it as long or short as I want and then use a negative value of t and make it go in the other direction. So that this -3/2 1 times t expression represents any vector that starts here and goes to a point on this line. So a vector from here to here, a vector from here to here, any vector that starts at the origin, goes to a point in that line, is going to be one of these. We call that line, well, we call this set of vectors a subspace of our R2, our two-dimensional space. This line represents a one-dimensional subspace of R2. Watermark might get that, but there it is. Now, as regards solutions to this equation, the solutions to this equation all lie on a line parallel to this line through the points 6, 0. There are many other points we could use, but now I haven't really left myself room for 6, 0 if I'm going to keep everything to scale. We're going to understand that this point is going to represent 6, 0, and we can draw the vector -3/2 1 at the point -6, 0. Vector is going to look exactly like it did over here, and wish me luck in getting that to happen when I'm looking from this angle. And then that vector multiplied by any old t gives us this. Now, this isn't a subspace of R2 because it's not closed under vector addition. Because in our convention for representing vectors in R2, the vector always starts at the origin. Okay, so if I have a vector from here to here and a vector from here to here, they don't add to a vector on this line. Now, we sometimes use the word an affine subspace, but that's a much more general idea that we're not going to talk much about at all in this course. Okay, so make sure we understand the insights that we get from this analysis. Now we can do a solution to an equation in 3 variables, which could correspond, of course, to X, Y, Z space. So that we, if we want to think about the geometric connection, and let me move this over a bit. I think we'll still be able to see it, so the watermark doesn't interfere. But we could have like X1 here, X2 on this axis, X3 on this axis instead of X, Y, and Z. So here we have a single equation in 3 variables. Okay, well, that means that for any 2 of the variables that I want to choose, I can determine the value of the third. If I tell you x2 is 47 and x3 is negative 398, you can easily do the arithmetic to determine what x1 would have to be. Very easy. Or if we wanted to let x1 and x2 be chosen arbitrarily, well, that means we'd be regarding x1 and x2 as free variables. And we could easily determine x3. Now, the way I choose to solve this is we're going to choose x2 and x3 to be our free variables with the solution to this equation in terms of x1. Now, clearly, if I didn't solve that right, I didn't divide by 2. Okay, I'm changing the equation. There it is. Okay, there's the equation. Now, the solution to the equation is this, because, of course, x1 is going to be 12 minus 3x2 plus 4x3. And if x2 is s and x3 is t, 2 parameters that are going to become arbitrary, then this is our solution. And this solution, we can do something very similar to what we did with the previous solution. We can write then x1, x2, x3 equals, x1 is going to be this, so there it is, x1 equals this. x2 is our s parameter, x3 is our t parameter. And now we can separate this out into 2 vectors, one depending on s, one depending on t, plus a third vector that doesn't depend on either of those. Okay, so clearly, if I add this to this to this, I get this. It should then be clear how if I have an expression like this, I can separate it like so. That's very simple, very obvious. So I'm not going to go into a lot of explanation. Then, of course, I can factor the s out of this, get s times negative 310, and factor t, and I'll get t times 401. And now, what does that tell us? Well, ignoring the 1200 for the moment, all the vectors I can get by multiplying negative 310 by s lie on a line. Well, the vector negative 310. Okay, that means x1, x2, x3. So we come over negative 1, negative 2, negative 3 units in the x1 direction. And in the x2 direction, we come over 1 unit, which is going to put us here. We have this little rectangle here, and here is our vector negative 310. And we can see that it's in the plane of x1 and x2. It's down here flat. We haven't come up above the plane at all. That's a pretty badly drawn arrowhead, but we have to live with it. Okay, so here we have the vector negative 310. And then we have the vector 401. Now 4 means 4 in the x1 along the x1 axis. 0, of course, means 0. And 1 means we come up 1 unit on the x3 axis. So we can kind of draw this rectangle here. And not very clearly drawn, but x3, sorry, the 401 vector is here. Now those 2 vectors, well, Okay, now any multiple of the negative 3, 0, 1 vector lies along the line here, and the line would extend here. I didn't do a very good job of choosing my vectors from my perspective. The vectors here lie along this line, and I'm kind of cheating to curve it upward a little bit, but it's a straight line. This line stays in the plane of x1 and x2. This line rises gradually above the plane, but along the x1, well, within the x1, x3 coordinate plane, within the two-dimensional plane with these two axes. Okay. So we can sort of visualize. I could have probably chosen better numbers to use up here to be more illustrative. I didn't think that far ahead. We can then form any vector we wish. Well, okay. We can add any two vectors represented by vectors in this plane, like this vector here. Sorry. We can add a vector on the line defined by s times negative 3, 1, 0. In other words, a multiple of negative 3, 1, 0. We can add any multiple of negative 3, 1, 0, for example, this one, to any multiple of 4, 0, 1, maybe this vector. So if we add that vector to this vector, we get another vector. And I'm not going to even try to sketch that because I had such a bad choice of numbers here. By doing that, I can get any vector in the plane of this vector and this vector. By the plane of this vector and this vector, I mean, okay, this vector is flat. It goes off in about that direction. This vector is not quite flat. It comes out this way, but also up. So we've got something flat here, something comes up here. We can imagine taking a sheet of glass and setting it down on those two vectors. It'll lie flat across the two vectors and it'll be kind of oriented like this. Okay, well, that's a plane. Then we get a solution of this equation if we come up to the point okay, I'm going to use a specific vector. I'm going to have to go right through my x3 label. Okay, let's say this vector is 12, 0, 0. Then adding any vector in this plane to this vector gives us a solution to this equation, so that the solution of this equation can be represented in 3 dimensions by this plane. Okay, a plane through this point is parallel to the plane defined by these two vectors. So there's a geometric interpretation, and we really do want our geometric interpretations. Okay. We can do geometric interpretations in R2 and R3, 2 and 3 dimensions. Our intuition doesn't go beyond 3 dimensions. We live in 3-dimensional space. And when we try to think in terms of higher dimensional spaces above 3 dimensions, we kind of rely on our intuition about lines and planes and 3-dimensional space. Okay, now let's say we have 2 equations in 3 unknowns, x1, x2, and x3. Well, here's first equation. And I'm not going to go through all the steps of solving it, just from here to here, I've kept the first equation, well, I've divided the first equation by 2, everything by 2. And then I've added the first equation that I got here to the second equation that I had up here. I've added 4 times the first equation to this second equation to get this. And I don't even guarantee I did my arithmetic correctly. That's not really going to matter for purposes of illustration. I'll try to do it correctly, but you never know. Okay, then I simplified this second equation. Might not look simpler because now we've got denominators and stuff, but the simplification is I've got a 1 in front of x2, which is going to be handy. I divided this equation, in other words, by 10, and got this so that now I can subtract 3 times this equation from the first and get rid of my x2. And that's what I've done here. Let's pretend I've done it right. You can check me if you want. And I now get these 2 equations. Now this is a familiar process. And of course, this can be done by augmented matrices. If I've done this correctly, we could write this out as 2, 6, -9, augmented with 18, and -4, -2, 3, augmented with -12. And 18 looks pretty bad, so I'm trying to make it worse. Okay, I managed. Okay, so we have this. And if we just follow the same operations, they're calling them row operations now. If I've done this correctly, we get 1, 0, 54 tenths, -9, 0, 1, -33 tenths, 6. And this stands for this. We can read from here, or we can read from here. In terms of now x3 equals t, looking at this form, so we're going to have 54 tenths t. Let's subtract that from both sides. And we're going to find that x1 is -9 minus 54 tenths t. And x2, similarly, is going to be 6 plus 33 tenths t, and x3 is just going to be t, which means now that this is this expression can be written as 960. Those are the only numbers we have that aren't multiplied by t, plus, and I'm going to not belabor it with a bunch of different steps, -54 tenths t, 33 tenths, and 1 t. So we have t times -54 over 10. (33 over 10, 1). So there we have it. Now there's an interpretation to this, and we'll talk about that in a minute. But we see the process, and the interpretation. We'll actually maybe draw this out. Didn't leave myself room in this board, but we'll draw it out on another one. Matter of fact, let's just go ahead and draw it out here. The interpretation is, again, we have t times a vector in 3-dimensional space. That's like 5.4, -5.4, 3.31. So we can draw that vector in 3-dimensional space. Okay, we come -54 tenths, that's about -5 on the x1 axis, 1, 2, 3, 4, 5. And then here's 6, so we come to about here. 33 tenths in the x2 direction, so that would be 3.3. So that would be about here. And then 1 unit here. And what we do then is we come out this far on the X1 axis, this far on the X2 axis, which brings us to this point. And then we've also got to come up 1 unit here. So I can sketch lightly a kind of a rectangular solid, like so. So this is like about that thick, this wide, this long. And this vector start at the origin and end at the far diagonal. So this vector is our vector, and I'm going to use decimals this time. Let's say we're going up to 9.6, so it's going to be up about there. So I'm going to label it down here. Okay. Now, looked at the 960 vector and I wanted to write it. I'm going to write this in decimal form because it's a little more compact. -5.4, -3.31. Again, this vector can be multiplied by t, by any number t, and it's going to give us a line through this corner and this corner of this rectangular solid. Then if I want the solution to the equation, I've got to come up to the point 960, which will be, 9 might be up here, 6 will be over here someplace. So here's my vector. Made no sense, of course. The 9's along the x-axis, so 9 would be maybe out here. 6 would be over here. So 9, 6, maybe be about here. So the vector 960 would be here. And now the solutions will all lie along a line parallel to the line defined by this vector through this point. Now, can't really tell the direction of that line except I'm saying it's parallel to this one. And from this rectangular slab that I drew here, you can kind of tell what the direction of this one is. So all the solutions are on this line, meaning that all solutions are represented by vectors from the origin out to this line. Okay, so these are solution vectors. In the sense that if I take the x1, x2, and x3 coordinates or components of each vector and plug them in to both of these equations, both equations will be satisfied. Make sure you completely understand that statement. Again, take the components of any one of these vectors that goes from the origin out to any point on this line, plug those components in for the x1, x3, x1, x2, x3 components plugged in to this equation will satisfy it, give you 18 on this side. And plugged into this equation, those same x1, x2, x3 coordinates will end up giving you the negative 12. You'll satisfy both equations. I hope what I just said confused you a little bit, because it was the last little thing I said was completely wrong. I focused on this line. I've done that in previous. We get not a line through this point, 960. We get a plane through this end of this vector. The plane being parallel to the plane that we formed no? Okay, I'm sorry. Thought I said something wrong. Let me just sort that out and I'll be right back. Now, if we take our system of equations, which of course can be written as a matrix equation in the obvious way, make sure you see all the details of how this system is the same as this matrix equation. In any case, we take this system and change it so that the numbers on the other side of the equal sign are 0. Then we get what's called a homogeneous system. It's homogeneous. We don't have any numbers floating around here except numbers that are attached to our variables, numbers that are coefficients of our variables, if you want to be more specific. So here's a homogeneous system. It's the homogeneous system for the original system of equations. If we solve the homogeneous system, we can eliminate x1 by the same technique we did before. The exact same steps that we used previously applied to this homogeneous system give us exactly the same left-hand side. Nothing on the right-hand side had anything to do with what happened on the left-hand side when we went through this process. Same's going to be true here. The big change is if we have a homogeneous system, we don't have any numbers here to add. We only have zeros here. So when we add multiples of one row to another or multiply a row by some number, it doesn't change the fact that we've got zeros over here. So at the end, we're just going to have zeros. So the system is going to reduce by the same steps, but we know what we're going to get over here. It's always going to be 0, and that has important implications. Okay, so now letting, of course, x3 be our free variable and letting t stand for x3, we get our solution. The x1, x2, x3 vector is just going to be t times this negative 54 tenths, 33 tenths, 1 vector. In other words, the same vector that we got over here, but this vector, we don't have the 18 and the negative 12, so we're not going to get a negative 9, 6, 0. We're just going to get all zeros here. So this vector is going to be 0, 0, 0. And I did write it out in this solution, and I suppose I could have, just to emphasize it. It's very important to understand now that any one of these solutions has to lie on this line through the origin, the line that we got over here, before we added it to the 960. Okay, here are the solutions of this system. Here are, and always were, the solutions to our homogeneous system. Now, the big deal about the solution to the homogeneous system is it gives you a subspace of R3. Okay. It's all the vectors are on a line through the origin. And if you add any of those two vectors, you get another vector on the line through the origin. Okay, so this thing is a subspace. Now, there are other properties of subspaces, but you can easily prove that this set of vectors is a subspace. It's a one-dimensional subspace. It's a line in R3, a line through the origin. Okay, now there's all the vectors rooted at the origin that lie on this line can be added to any other vector rooted at the origin that lies in the line, and you get another vector rooted at the origin that lies on the line. And multiples of those vectors still lie on the line. All the properties of vector spaces are satisfied by vectors that can be represented on this line through the origin. Not true of the vectors that you get out to this line, which is a set of solutions of this equation. Okay, solutions of this equation are displaced from this line by the 960 vector. So you take any point on this line and displace it by vector 960, you get a point on this line, and every point on this line is displaced by the 960 displacement for a point on this line. Okay. Now we're going to use a little more advanced terminology, since this is by way of review from midterm exam. This line through the origin is what we call the null space corresponding to this matrix. Okay, so here we got this line through the origin. I'm going to go ahead and make it red. Yeah, we'll kind of keep a little red in there. Screw the blue vector, okay? This is the null space corresponding to this transformation, and more specifically corresponding to this matrix, because everything that we do here can be done in a way that everybody should understand by now, by matrix operations on this matrix. So we could call this the null space of our coefficient matrix 2, 6, -9, -4, -2, 3. We could also talk about the row space of this matrix. And I don't want to do that just right now, but you can kind of see how that's going to work out. Yeah, I said I wasn't going to talk about it. I'm going to talk about it. See how that fits into our picture. The row space of this matrix is the same as the row space we get if we reduce the matrix. And as we saw previously, this matrix reduces to this. So let's just see what we gain from that. Okay, so this matrix reduces to the matrix 1, 0, 54 tenths, 0, 1, -33 tenths. And you might be wondering why don't I just call that 5.4 and 3.3? I certainly could. But in general, you're not going to get anything that reduces to a simple decimal form like that. So I'm just kind of keeping the calculations general. Okay, so anyhow, this matrix reduces to this. The row space is the set of vectors that are spanned by the two rows. Okay, so adding multiples of those two rows to one another, or multiplying a row by a number, or if we reverse, switch two rows, doesn't change the space that's spanned by the two row vectors. Okay, if you add two vectors in a vector space, and the span of these two vectors is a subspace of R3. If you add two vectors in a subspace, you get another vector in the subspace. So if you're always getting vectors in the subspace, you're still spanning that subspace. There's a little more to say what I said, but that's the idea. Okay, so this reduces to this. Row space is then spanned by these two vectors. And I'm going to go ahead and use the decimal equivalents. But the row space and I can say that it has a basis. Okay, we have two linearly independent vectors here. These are linearly independent, and they span the row space, and there are only two vectors that define the row space. You can think about why that makes this a basis. The row space, skipping a little bit here, but a row space has basis 1, 0, 5.4, 0, 1, 3.3. How do those vectors relate to what we see here? Well, 1, 0, 5.4, that's like it comes out here, it doesn't go over here, it comes up here. So that vector is like right here, pointing up kind of in this direction. And 0, 1, 3.3, well, we have 1 here and we have 3.3 up here. So it's in the x2, x3 plane about here. There's more to say about it, but I'm going to stop there because I don't have a good picture. Actually, I want to think for a minute about whether I do want to say something. So I'm going to pause for a second. Okay, as I said earlier, I could have some arithmetic errors, and I just discovered one because something wasn't making sense in my picture, which is one of the reasons I didn't want to go on with it. And because I'd already made an important point, but let's see if we can patch this up a little bit. And I'm not going to try to correct the arithmetic because it would cause me to have to redraw everything. Let me explain. When I started this video, I didn't know where it was going to go. Okay, I'm trying to relate things to where we are in the course, and I planned out to, well, actually got a set of problems that I planned this around. But I kind of like to do this not knowing where I'm going to go for a couple of reasons. Once I've done something, then it becomes clear where I want to go next. Another reason is I make errors and I find the errors in the process. Okay, I don't intentionally make errors, but you see what error I made here. It's very easy to make these errors. It then allows us to see the necessity for always looking at what we've got and checking it, okay? And I got to the point which would have made a good check, actually did make a good check, even though I wasn't thinking about checking. So these general pictures, everything is valid, except some of the numbers are screwed up. Okay, and that eventually caught up with me when I went to the row space thing. Didn't know I was going to go there with this, but I'm kind of glad I did. Okay, now back to the error. A couple of errors. Yeah, like one, I have a negative in front of this line. I don't have one in front of this, do I? Okay, so that kind of changes where this vector would be, but it doesn't change the idea of the picture. Another thing is that here, I added twice this to get this, to get rid of the x1. I added twice this to get the 10x2. Then I added 4 times this to get the negative 33. Okay, should have added 2 times this, not 4 times this. And that really kind of messed a lot of things up. Okay, so if I'd added 2 times, I'd have had a negative 15 here. And it would have made this still negative and made this still negative, which would have not caused me to see something that didn't look right when I drew that last picture. So with all that, you're welcome to fix this. It would be a great exercise. It's not that difficult. The arithmetic is very simple. And of course, you can always go online and reduce the matrix and get it all right. Okay. And of course, this picture would change a little bit because that negative 33/10 wouldn't be there anymore. But we're just going to go on with it. Okay, because the numbers are not that important to the process and to the insights. The thing that bothered me down here is that both of these vectors should be perpendicular or orthogonal to this vector. Now, I know that you don't, and you won't understand that until we get into the next chapter on inner product space, actually, chapter after next on inner product spaces. Although it's very easy, if you understand dot products, which you might if you've had all the complete prerequisite courses, you might. As it turns out, this vector is orthogonal to this vector. This vector isn't, but would be if I change the sign of one of these, but I can't do that. Really, the only way it's going to work out is if everything was done correctly. Okay. The upshot of this is that the span of these 2 vectors should be perpendicular to this line. Okay, so what you have is 2 perpendicular subspaces. You have a line perpendicular to a plane. So you have a plane here. Well, you've got a line. Here's your null space. And now you've got this plane. And the line intersects the plane at some point. And the line is always perpendicular to any line in the plane. It's not well drawn. There should be some dotted lines in there and stuff. But the null space is perpendicular to the plane. In this case, the null space is a line, plane, and that's the row space. And that all works out pretty nicely if you just fix the numbers. Okay, well, that's a big deal. You have no idea how big a deal this is. You won't for a couple of months yet. Actually, a couple of months will be at the end of the course, at least 4 to 6 weeks before you really see how neat this is. Okay, So that's where I was going with this: row space, null space, or orthogonal, perpendicular. Orthogonal and perpendicular mean the same thing when you're in R3. But if you want to say that this polynomial is perpendicular to that polynomial, you can't say it. You got to say orthogonal, because perpendicular doesn't make sense in some vector spaces. This matrix is perpendicular to that matrix, doesn't make sense, but we can say it's orthogonal. Okay, well, that's terminology. You kind of store that away. It doesn't hurt you to hear it right now. So where we are is we've got a system that has a solution, and the point I need to make, and made previously, the point you want to take away here is that the solutions of the original system can be written as solutions of the null space plus this solution. Okay, and that's what I want to talk about just a little bit next. Okay, now here's the big deal, or something that is a big deal. There are many big deals in linear algebra, but it's a pretty big deal. Okay. Here's your null space. Here is our solution. We're going to call this any particular solution. Meaning any solution to this equation for any vector B over here. Okay, again, big deal. Here's your null space. Here is any particular solution. For example, if 960 really was a solution to the equation, negative 960 would be. But any particular solution to the equation, then if you draw a line parallel to the null space, and for convenience, I'll go ahead and put a set of coordinate axes here. Then any vector from the origin to this line all the green arrows represent solutions. Now I said something over here because I wasn't thinking, and it really kind of is regrettable that I said it. I said all solutions lie on this line. That's not true. Solutions of the equation lie plane. What I should have said was all vectors to the line, implicitly, all vectors rooted at the origin to the line represent solutions. Okay. So in a sense, this whole line represents a space of solutions, but not really, because it's not really a subspace. All the lines that you get by displacing by any particular solution, I didn't say what a particular solution is. Okay, let me digress. A particular solution is any solution of this equation for any result. Okay. So a particular solution it's a solution of this equation for any vector b over here. So for the vector b equals 18, negative 12, the solution should have been negative 960. So you would have that particular solution. You displace every vector in the null space by that vector, and you get a line representing another bunch of solutions. Okay. There's a statement that can be made corresponding to this picture. So I'm going to set up a board here so you don't have to watch me do that, and we'll do that. Okay, so stating what we did just in terms of symbols, we can generally say if x sub p is a solution to ax equals b, where this could be any system of equations, not just a system of two equations and three unknowns, any system of m equations and n unknowns, then we call this a particular solution. It's any solution of the equation. And bring this over a little bit so it's clear. If we add any vector in the null space to the vector representing the particular solution, we still get a solution. Okay. Now that's what we indicated geometrically. The geometric picture helps us picture what this is, and a picture helps us think about the things we need to think about in order to approach a problem or a situation. So this is important, and I'll just say there's a proof of this, and I think that's probably in the upcoming section. The reason for this is implicit in the elimination process, since the elimination process is the same for any b, including b equals 0. Now, by the elimination process, I mean the elimination process in solving either the matrix equation here by reducing the matrix, augmented matrix. If you write the augmented matrix, what you do over here is not affected by the numbers you augment the matrix with. Those numbers just go along with the process of reducing the original matrix. And if you go back to the solution of the equations, as we said, this left-hand side has no dependence on what's on the right-hand side. So if you've got all zeros on the right-hand side, you get all zeros here, and that's why this actually works. Okay, well, that starts with solving a simple linear equation, it moves us all the way up to the idea of rank and nullity. Then, of course, there are more details in rank and nullity that we'll talk about later.